It's time now to talk about light and how astronomers use light to make discoveries in our universe and solar system. Pose a question for you. Suppose the stars did not emit light. How would we learn about them, discover their properties? Well, we'd likely have to travel there, which would, with today's technology, not be possible to have a productive scientific mission. So astronomers are going to use light to learn about the properties of stars, and we can sense various things about the stars and the planets: temperature, composition, or what elements are there, or just some of the items that can be determined by the study of light. Magnetic field, many interesting facts about our universe, fortunately, are available to be learned by the study of light from objects in the universe. So it is very important to have a solid foundation on how light behaves and how it can be used to provide us with information. So what is light? Well, in the 1800s, electricity and magnetism were investigated, and in about 1865, a theory of light was proposed that modeled light as vibrating electric and magnetic fields, if you want to think of it, electric and magnetic forces. So we have these arrows represented here, and the situation is we have an electromagnetic wave traveling through space. This wave has an electric field, let's say with the red, and a magnetic field with the blue, and we can't see this directly with our eyes, but we detect light. This wave is carrying energy, and it has the ability to influence receptors in our eye, and we can see. The other aspect to this is that this is the wave model where light is traveling from one place to another. There's another model for light when light is emitted or absorbed, the photon model, and I might mention that briefly later on. But the wave model is appropriate when light is traveling from one place to another through space. Light is traveling as an electromagnetic wave. So we know about water waves. We have to have a medium, we have to have water for water waves to go from point A to point B. Sound waves, if we have air or if we have a liquid or a solid, the sound can travel from A to B, but sound does not travel in space. It does not travel through a vacuum. Sound needs a medium. Light waves are different in this respect to water and sound waves. Light waves can travel through a vacuum. There is no medium required for light to travel from point A to point B. Light can also pass through a medium. It can pass through water, it can pass through glass, pass through air, but it can do this very special thing, travel through a vacuum where there's no material. Water waves and sound waves, waves on a rope, they need a medium. The speed of light is also very special. It's extremely fast. It's about 1,000,000 times faster than the speed of sound. Not quite 1,000,000, but just for rough numbers, light is about 1,000,000 times faster than the speed of sound. So the electromagnetic spectrum can be identified. Scientists have created these names for different wavelengths of light, and also there are different frequencies of light that goes hand in hand. When we have a short wavelength off here to the right in the gamma ray part of the spectrum, we have a high frequency, and we also have high energy. Gamma rays and X-rays are hazardous and have to be used in a controlled way. Radio waves are not dangerous, so we can allow radio stations to send radio waves across the city. We would not allow a transmitter of gamma rays to be inside a city, or a transmitter of X-rays to be inside a city. Short wavelength is high frequency. High frequency means high energy. And again, this kind of scale of these wavelengths, radio waves can be the size of buildings from peak to peak. Microwaves, size of a person. Infrared, the size of the pinhead, then the visible spectrum, the ultraviolet, the X-ray, we're getting down to the size of atoms, and gamma rays getting to the size of the nucleus of an atom. So we have this electromagnetic spectrum. You should be aware that there's a change in energy, with the highest energy being gamma rays, X-rays, the lowest energy being the radio and the microwave end of the spectrum. So electromagnetic spectrum, different types of light, the different energies, the different frequencies have different interactions with materials. In the visible spectrum, we have a sequence here from red to violet. Some people memorize the progression of the colors here with Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. Hopefully you can use this or some other pattern, but you do need to memorize the sequence of the colors across the visible spectrum. And you need to know that red has the longest wavelength, violet has the shortest wavelength. Which color has the greatest energy? Red or violet? And you should be saying violet because short wavelength goes with high frequency, and high frequency goes with high energy. And just beyond the violet is ultraviolet, and then X-rays. So that's the high energy end. To the long wavelength side of red light, we have infrared light. Your TV remote control uses infrared light. It's not hazardous. It's not a laser. It's infrared light. So suppose we want to see the different colors present in a beam of light. So we have white light here coming into this prism. As light passes through a glass, it turns out that the different colors have different speeds in the glass. They all have about the same speed in air, but when the light passes through glass, the different colors refract different amounts. They get bent through different angles. And the colors get spread out into a spectrum, with the red not being bent as much, with the violet being bent the most. So a prism can separate the colors, and this was done in the late 1600s, and scientists started to investigate the electromagnetic spectrum and how much energy was present at different colors from different objects. So the prism can spread out the colors and make them more accessible to study individual colors. And this is further enhanced with another apparatus called the Diffraction Grating. It actually does a better job of separating the colors than a prism, and it's just a more reliable way of determining colors because we can spread the colors out more. It's a better way of investigating the light that comes from planets or stars, so we can see more details when we use the diffraction grating to spread out the colors. So prisms spread out the colors a little bit, diffraction grating spreads out the colors more, and help astronomers make more detailed investigations of the light. So again, you should hopefully see a demonstration of this, or click on YouTube, do your own search for prism or diffraction grating. And I should mention too, all these colors of light, the red through the violet, gamma rays, radio waves, they all travel with the same speed through a vacuum. There is one speed of light that covers all the different types of light. The different types of light have different energies. The short wavelength has high energy, the longer wavelength has less energy. As we look at objects that are emitting light, we can notice that there is a regular progression in the spectra coming from these objects. A black body is an object that's a perfect absorber. The black body also emits light, and we can see this a little bit in a hot wire that is heated to different temperatures by a different amount of electric current passing through the wire. But if we have just a little bit of current going through the bulb, it might have a temperature of 300 Kelvin. The Kelvin is the scientific unit of temperature. At 0 Kelvin, that's absolute zero. 300 Kelvin, that's a little bit above room temperature. Room temperature is about 20 degrees Celsius, and you add 273 to find the Kelvin number. So 293 is room temperature roughly. 300 Kelvin is roughly room temperature. So if we were to have a black body, just a piece of wire laid on a table, it turns out it does emit light, not very much light. See, the curve is low here. Over on the left is sort of how much energy is coming off of the object at each color. So we have a little bit of energy, and we have a peak out here that's out in the long wavelengths, way beyond the red, long wavelengths, infrared and even a little bit longer. As we cause the temperature of the wire to increase, if we run more current through the wire to 500 Kelvin, notice that there's more energy being emitted at every wavelength, and the peak of this curve shifts to shorter wavelengths. This continues for 1000 Kelvin, and finally the 2000 Kelvin, the last one on this graph. And now at the 2000 Kelvin, we have a useful light bulb. Out here is our visible spectrum, and the light bulb is providing energy at the visible light wavelengths. Notice too, though, there's a lot of energy that's emitted out in the infrared, and that's one reason that the incandescent, the hot wire type of light bulbs, are being phased out in favor of LED lights or other arrangements that emit light more efficiently, put more energy into the visible spectrum, and waste less energy out in the infrared where the human eye cannot see it. But again, notice the progression. If the object is hotter, then we get more energy at every wavelength, more energy emitted, and the peak wavelength shifts towards the shorter wavelengths. Now 2000 Kelvin, that's not hot for a star. It's fairly hot for a planet, but not hot for a star. The stars, this progress, this pattern continues until even the peaks are out in the ultraviolet instead of in the visible spectrum. But the blackbody spectrum, we have an object, likely a solid or a liquid or a very dense gas, can emit this type of spectrum. Scientists can measure the energy coming from the object, determine where this peak occurs, and that gives a clue as to what the temperature of the object is. The wavelength where this peak occurs is related to the temperature of the object. We're not going to calculate that for my class, but you should know that the peak wavelength is related to the temperature, peak wavelength being the highest point of this curve. As we look at some sources, we find that there's not energy at every color, but instead there's energy just at selected colors. And this is called an emission spectrum. When we have energy emitted by the object just at certain wavelengths, at certain colors, this is an emission spectrum. If we investigate different elements, hydrogen, carbon, oxygen, iron, sodium, calcium, etc., what we find is that the pattern changes for each element. The wavelengths where there's energy being emitted is different for hydrogen compared to carbon, compared to helium, compared to oxygen, compared to iron. This enables astronomers and physicists to look at a spectrum and record the wavelengths where energy is being emitted, and then look up in a table of studied elements, find a match for the wavelengths, and the element that's emitting the light can be identified. So an emission spectrum. It's a line spectrum. You get these bright lines when the diffraction grating spreads out the colors. We get this line spectrum. Tells us that we have a thin gas that's emitting the light, not a solid, not a liquid, not a dense gas, but a thin gas will have this characteristic spectrum called the emission spectrum. And again, if we change the elements, the pattern of the lines here would change as well. Our third type of spectrum is the absorption spectrum. The absorption spectrum. So across in the background here, we see the colors from red to violet. that would be the continuous spectrum from some black body giving us light at every color. But if there is a cool, thin cloud of gas between us and the black body, that thin cloud of gas can absorb light at certain wavelengths, leaving dark lines present. So there's light coming from a distant object passing through the thin gas. The atoms in that thin gas absorb energy at certain wavelengths and leaving then less energy to continue on to the observer. So the absorption spectrum created when we have a source of a continuous spectrum, a black body in the distant background, and we have this thin gas in between us and the black body. So there's another slide of this coming in just a minute, but there's an important consideration for the wavelengths. What do you notice about the wavelengths or colors of the emission lines and the wavelengths where the absorption lines are located? You should notice that the wavelength is the same for emission and absorption. The wavelength of the emission lines match the wavelength of the absorption lines. There's a good reason for this. In the emission spectrum, what is happening is an electron is dropping down to a lower orbit near the nucleus. That electron is giving up energy, and that energy becomes light. That's the emission process from an atom. An electron moves from an upper level to a lower level, and that energy difference is sent out of the atom as light. For the absorption process, light is coming into the atom, lots of different wavelengths here, but there'll be a particular wavelength that this light has an energy that matches a gap in energy between two electron orbits. The electron can absorb that light, and the electron then moves to an upper energy level. The absorption process, we have light of a particular wavelength. That makes it probable to be absorbed by the electron in the lower energy level. The electron then absorbs that energy and moves to an upper energy level. Light that does not have the proper wavelength does not get absorbed. So if the light has too small of an energy, a long wavelength, if it has too much energy, too short of a wavelength, there's not a match between the energy of the light and the energy gap for the electron. And the electron ignores that light coming by. An interesting fact about emission lines and absorption lines, if we have the same element in this thin gas cloud that's emitting light, same element as we have in this gas cloud, this thin gas cloud that's absorbing some light from the distant black body, will have the same wavelengths for emission and absorption. As long as the element is the same, the wavelengths will be the same. If we change the element, both patterns would change. Where the bright lines are located and where the dark lines are located again would line up, but they would be in different positions compared to this element. So same wavelengths for emission and absorption lines as long as the element is the same. Oh, here's a little chart of showing the production of the different types of spectra. Really, we're talking about what's called Kirchhoff's laws of spectra here. If we look at a hot source, a solid, or a liquid, or a dense gas, then we observe this continuous spectrum, all the wavelengths of light being produced. If we look at a hot, thin gas cloud, so we're looking at light just from this object, we're not looking at light from the spectra, that's the spectra of the black body. But if we look at light coming from this hot, thin gas cloud, what we find is an emission spectrum. And again, the pattern of where the energy is located in wavelength is unique for each element. This spectrum is really like a fingerprint. Each element has a different pattern of these lines. It's a fingerprint, and astronomers can look at the spectrum, and by measuring the wavelengths of what emission lines are present, astronomers can find out what elements were in this hot gas cloud. Whether they're in the solar system, or if they're in our galaxy, or if they're in some other galaxy, astronomers can look at the spectrum of light and determine what elements are present. Astronomers can also determine what elements are present by looking at the absorption spectrum. So here we have this hot source that's emitting a continuous spectrum, all the colors. That, that light is passing through a cool gas cloud. Inside here, certain wavelengths are able to be absorbed. They have energy. The wavelength of light has a certain energy that matches the energy gap between a lower electron orbit and an upper electron orbit. The electron absorbs that energy, taking away energy from the continuous spectrum that's continuing on to the observer over here. So we have these dark lines, the absorption spectrum. And again, by measuring the wavelengths of the absorption spectrum, astronomers can determine what elements are present. And by measuring how dark the line is, astronomers can get an idea of the abundance of a particular element. If the lines are darker, there's more of the element present. There's some other technical details, but that's the summary. If the absorption lines are darker, then there are more atoms that are absorbing energy and taking it out. You might ask, what happens to this stored energy as the electrons go to an upper energy level? Well, there's a certain probability the electron will drop to a lower energy level. When it does so, that light comes off in random directions. The beam of light that's headed towards us, as these electrons drop back down to a lower orbit and emit light, that light is not directed in the same way that it came into the gas cloud. That light has some random direction, and if some observer is over here and looking at this gas cloud, this observer will see an emission spectrum because they don't have this continuous source of light behind to have that light be absorbed. So they just see the light that's being emitted by the atoms. We have to be in a special position. We have to be an observer here where the cool gas cloud is in between us and the black body. If we're observing up from this position, looking at that gas cloud, there's no black body down here. We do not see an absorption spectrum. Instead, we see the emission spectrum. Here's a spectra to take a look at. And we have a peak to the spectrum. And these are emission lines, these little descending parts in the white. Again, created by different elements in the star. This is a star spectrum. So we have a certain amount of energy being given off at each wavelength. Stars are basically black bodies. They have light emitted at all the colors, but the stars have an atmosphere around them, a thin gas, and that thin gas can absorb light at certain wavelengths and create these absorption lines, and then the astronomers can study that and determine what elements are in the atmosphere of the stars. We do not have to go to the stars or the planets to determine what elements are in their atmospheres. We can study the light that comes from these objects and learn what elements are in planets and what elements are in stars. So here's kind of a summary. This electromagnetic wave is light. There is an electromagnetic spectrum, the gamma rays at the high energy end, the radio waves at the low energy end. The speed of light is extremely fast compared to anything that you're used to, 1,000,000 times faster roughly than sound. And we have no rockets, or planes, or bullets, or anything that travels near the speed of light. We can make objects travel near the speed of light, like a single electron or a proton, in a laboratory. But as far as some vehicle to transport people or cargo, all of our technology is very slow compared to the speed of light. So, for example, the Apollo astronauts, it took them about 3 days to go to the moon. It's about 1 second for the light travel time to go from the Earth to the moon. Okay, again, the energy is related to the wavelength. You should be memorizing the colors in the visible spectrum, the Roy G. Biv. And light can be used to give us information on temperatures of objects and the elements that are present in objects. Again, I might just say a brief word about the photon model of light. Einstein won the Nobel Prize for his explanation that when light is emitted or absorbed, the light acts like a concentrated package of energy, not spread out as a wave, but a localized package of energy that we call the photon. So that's when light is emitted or absorbed. While light is traveling, it does act like a wave. It does not act like a particle or a localized package of energy. So light travels as a wave. And I'll pose a question to you. Suppose we have a couple of objects. One has a temperature of 5,000 Kelvin. Another has a temperature of 8,000 Kelvin. Which object will appear to be more blue? An object that has a temperature of 5,000 Kelvin or an object that has a temperature of 8,000 Kelvin? Well, it's the 8,000 Kelvin object. If you remember from the graph, as the temperature increases, the peak wavelength shifts to shorter wavelengths. So our sun is about 5,800 Kelvin for its temperature, and it peaks in the yellow. So this temperature, object A, would have kind of a yellow-orange appearance. Object B is going to be bluer. Objects that are hotter have a shorter wavelength for their peak energy. So that controls our colors. So you should read through our online textbook, read through a reading guide, and write down some questions and ask those questions. But hope that you've learned something about light.